CFD simulations are said to be expensive and complicated. We are working to change that. An example is shown in this video. Our solution consists of two building blocks. The first building block is the use of open source software. Open source software is first of all free. Well-known open source software, for example, is Linux as an operating system or LibreOffice as a replacement for Microsoft Office. However, there are now also many open source programs for engineering applications. We concentrate on OpenFOAM for CFD simulations and CodeAster for finite element simulations. Both are very powerful programs that deliver reliable results. However, Linux, for example, as open source software, has the reputation of only being suitable for experts. Similarly, open source engineering programs have a reputation for being complicated to use. Therefore, the second building block is the automation of simulation. We have developed software that specifically supports the automation of simulations with open source software. It is called InsightCAE and is itself also an open source project. Strictly speaking, it is a framework, that is a collection of functions that help to create a program, the automated simulation. The simulation sequences themselves must of course be created problem-specifically. However, the InsightCAE distribution contains some sample simulation sequences, we call them workflows, that are already useful in many cases and that we want to use in the following. InsightCAE bundles everything needed for automated simulation and provides an API for the workflows. This includes first of all the administration of input parameters and result data. All input parameters of a simulation are combined to one parameter set. This can be edited in a graphical user interface, saved in a text file or loaded from a file. Alternatively, the simulation can also be started via a command line tool if no graphics screen is available, for example on an HPC cluster. InsightCAE also includes other tools that are useful in the development of automatic workflows, for example the OpenFOAM case builder, or for parametric geometry creation and editing, the script-based CAD program InsightCAE. These tools are each presented in their own videos. Using automated workflows with InsightCAE has a number of advantages. First, simulations can be run faster and productivity increases. Second, errors are avoided because the workflows naturally implement the best practice and the number of steps to be performed by the user is reduced, thus reducing the space for errors. Third, a standard for performing simulations is established and the results are prevented from becoming dependent on the user's habits. In a team that, for example, performs design tasks and in which not all members have experience using simulation tools, automated simulation can help to distribute tasks more evenly. Experienced users can maintain the simulation recipes and inexperienced users are able to use them in their projects. In teams without any experience with simulation tools at all, the creation and maintenance of workflows can be completely outsourced. In fact, this is also a service we offer as Silent Dynamics. How few steps are necessary for the user in the ideal case with an automated simulation, I want to show now. We want to solve a typical problem of external aerodynamics, we want to calculate the air resistance of a body. In this case, it's this car. Such a 3D CAD model has of course to be created and that is a task in itself. For this demo I simply downloaded the model from the internet. You can find such models for example on the GrabCAD website or in the 3D warehouse of SketchUp. In the present case, the 3D model is finally available in STL format. The STL format is very simple and can be exported by all common CAD tools. To create the simulation we now open the InsightCAE Workbench. This is the graphical interface used to edit the parameter sets for a simulation. The entry in the Start menu can be found in the section Education. A new analysis is created by selecting New from the Analysis menu or by pressing Ctrl+N. All existing workflows are listed in the following selection window. Our workflow can be found under the category Generic Analyses and is called Numerical Wind Tunnel. To create the new simulation, select the entry and confirm with OK. Now the input form for the parameters opens. On the left side there is a tree with the available parameters. Normally not all parameters have to be changed. However, some must always be adapted or at least checked because they are problem-specific. These are highlighted in yellow. The parameters that rarely need to be changed are shown in gray. A 3D graphics window is located on the right side of the form. There the geometric elements of the simulation are displayed so that you can check the correctness of the parameters whose influence can be visualized. If finally a parameter is selected in the left parameter list, a description of the parameter is displayed in the middle area of the window, and there are also the control elements with which the parameter can be changed. For our example, we first set the parameter objectFile. Select the parameter by mouse click, then the help for it and the corresponding input field appear. The button with the 3 dots opens the file selection dialog and we can select the file. The object is now displayed in the 3D window. The size of the flow domain is calculated from the object dimensions and displayed as a wire grid around the object. Next we change the inflow velocity. The parameter is called v in the operation section. The velocity is given in meters per second. We set 33 meters per second, which is about 120 kilometers per hour. A number of files and subdirectories will be created during the simulation run. Therefore it makes sense to run each simulation in a separate folder. This folder is set via the last parameter in the list named execution directory. The procedure is analogous to the selection of the geometry file. If the simulation is to run on a multiprocessor computer and several processors are free, it makes sense to use all of them to accelerate the simulation. The number of processors to be used can be set via the parameter NP in the section Run. The demo system has 4 processors. I would like to use them all, so I set the value to 4. Normally it is very important to create a good grid. There are some parameters that control the grid creation. Most important is the number of cells with which the object is resolved. They are set using the NX parameter in the Mesh section. The grid is refined by chopping the cells. You can change the minimum and maximum number of subdivisions applied to the cells on the object. These are the parameters min level and max level. Finding the right meshing parameters is an iterative process. You first start with a grid and look where further refinements are needed. The defaults are set to produce a relatively coarse grid. First I leave the default parameters. Now all parameters are set. I start the simulation by clicking on the Run button in the upper right corner. The first step is the grid generation. This will take some time. When meshing is finished, the flow solver starts. While the flow solver is running, the most important parameters that CFD specialists are usually interested in are displayed online in various diagrams. These include residuals and continuity errors, both of which should be as small as possible, and the forces and moments that will eventually become stationary and should no longer change. The simulation runs for 1000 iterations. If one recognizes beforehand that forces and moments have become stationary, one can enforce by clicking on the button Write plus Stop that output is written immediately and the solver stops afterwards and InsightCAE starts the evaluation. After the solving process, the evaluation is performed. The forces are extracted and the course over the iterations is displayed. Furthermore, different renderings are generated by ParaView. The results are displayed in the Results section of the Workbench. The produced results can also be written in a PDF report. To do this, click on Create Report in the Results menu. In the File Selection dialog, you can then select a storage location for the report. If the extension .tex is specified, a LaTeX document is written. If .pdf is specified, a PDF document is created directly. If the generated renderings do not suffice, you can also perform further evaluations with ParaView afterwards. The generated OpenFOAM case with all results is left in the execution directory of the simulation. A click on ParaView on the right side starts ParaView. In our example, I first extract the object's surface by applying the extract filter and only selecting the patch named object. Next, I add the streamlines filter. The streamlines filter needs a seed line to start the integration from. I put the line a little distance upstream from the object. By default, 1000 points are distributed evenly along the line. The integration of 1000 streamlines takes a little while. Once the integration is finished, we can now inspect the topology of the flow. The flow separation behind the car back is easily recognizable. At this point, my demonstration is finished. I hope you enjoyed it and I was able to show how easy a CFD simulation can be for a user when supported by workflow automation. InsightCAE is free software and can be used without any obligations or costs. You can find the source code at GitHub under the given link. Please also visit our website for more information about InsightCAE itself and how we can help you to use it. Thank you for watching. We look forward to get in touch with you.